Good afternoon and welcome to YELO's Burn-In and Life Test presentation. My name is Martin Collins from YELO Limited in Northern Ireland. YELO are based in Northern Ireland. We've been established in 1983. We're privately owned and we have 50 plus staff members. We design, manufacture and support laser diode reliability, burn-in, life test and characterization systems. In general, my discussion today is about why you need reliability, and the obvious reason is you need reliable optoelectronics devices in the field. So to be commercially successful, you must have reliable devices. In the early days of manufacturing, there was a huge failure rate due to manufacturing processes, misunderstood failure mechanisms, and manufacturing controls in optoelectronics. Today, we don't have that excuse for non-reliable devices. The manufacturing process has a much higher yield today, and this leads to the fact that lasers have been adopted in many different applications and equipment, and as such, the consequences of a premature laser failure can still be very expensive today. So what are the failure mechanisms that we would normally suggest as the main ones? So there's really two mechanisms that can cause a failure of a device. One is surface damage to the device due to the laser emitting light at a very high intensity from a very small area. And the two is device overheating. In both these cases, the deterioration of the device can be very slow or it can be catastrophic, i.e. immediate. So hence the reason why burn-in is of vital importance to the manufacturing and process stream for optoelectronic devices. Burn-in involves and allows the stressing of components under a continuous period of operation under controlled conditions with two primary goals. One is to identify the infant mortalities, and those are devices that will fail early due to manufacturing issues at the manufacturing stage. The second is the reality of stabilizing the operating parameters of the devices that pass mortality rate. So thus, this ensures that devices that are shipped from your factory will meet the quality standards that you're working to within your factory. So at what stage should we consider doing burn-in? And the consideration is one of cost. The earlier you can do burn-in within your manufacturing process, the more cost effective it will be for you. So in relation to this graph represents that the most early access to testing a device is at wafer level, and as such, that's the most cost effective. But as you go along the process manufacturing steps through singulating bare die, through to initial packaging in COC, through to more defined packaging such as butterfly, through to the device in the field, the cost of the burn-in in those stages increases quite dramatically. So the earlier access you get to burn-in, the more cost effective it is for you. But this leads to some challenges. And challenges today for equipment manufacturers such as YELO are that devices are getting smaller, and the amount of heat being asked to extract from a device during burn-in is getting larger. So you have a degree C per watt per millimeter squared challenge. The device miniaturization also lends itself to problems in terms of how to probe small electrical contact pads, and also in relation to downward force on the device to ensure proper thermal contact to the insulating plate or base plate. The base plate itself has manufacturing limitations on surface flatness. The ideal scenario is that you minimize your thermal resistance between bottom of your device and your base plate as much as possible, but manufacturing limitations do have a limit on the surface flatness that you can achieve. And this obviously is the main aim is to minimize the thermal resistance between the device and the base plate. Other challenges are output light management, and as devices become more complex, there's more challenging areas in how to extract the light and get it onto suitable photodetection arrays. So during burn-in, what does one use in burn-in, or what would one require? So in situ monitoring of current and light is a prerequisite. So a user may look to monitor the variation of light output over time under a constant current active basis, or they may look to monitor the variation of current over time under a constant power mode of operation. As well as those primary requirements, you then have the requirement that users would like to um, run LIV sweeps, that's light, current, and voltage measurements internally in the system without manual handling. And generally, that requirement also leads to a change in temperatures between differences between soak temperature and test temperature. And other measurements that may be requested or may be required would be in the area of spectrum. How is your device behaving spectrum wise under soak or burn-in conditions? So a burn-in system itself can range in terms of its end user requirement. In terms of YELO's product line, we have low power systems up to 1 amp. We offer high power systems up to 500 amps. We offer high density systems, high channel count systems up to maybe 5,000 systems per rack. And another important part of the whole process is to the characterization capability of the equipment. So we have laser diode characterization systems, which will offer you not only spectrum LIV, but far field, near field polarization. So depending on your manufacturing process and your devices, there's generally a different architecture suitable for your application. In terms of the tests that one may undertake, here's a couple of snaps of what systems can achieve. So as I said earlier, if the user wants to employ an LIV sweep at a regular interval, they may want to do that at a different temperature than the soak or burn-in temperature of the device. The example on the left, the graph on the left shows a device getting burned in at 90 degrees for a period of roughly 12 hours. And at that point of 12 hours, the temperature is dropped to 55 degrees. And what you'll find is that an LIV takes place at the bottom of that first drop in temperature. It automatically goes back up to 90 degrees after the completion of the LIV and will continue for another 12 hours. So that's called temperature cycling for LIV. Systems also would present threshold sweep voltages and graphs of user information that users always require to have a immediate access to devices. So the one on the right shows a 150 amp system with a threshold of roughly 25 to 30 amps, and the actual light output measured up to 150 amps. Other images are obviously another LIV sweep on the left hand side, where there's a single channel allocated just for low power LIV sweep. And on the right hand side, a graph which shows you the variation of the light output over time. So this is approaching the graph image of 1,000 hours test, where multiple channels, probably 32, are shown that they're monitored over the period of that close to 1,000 hours. In summary, just a bit of information about YELO. We YELO believe that time to market is of importance to the end user. Our systems are standard and flexible. In terms of production flexibility, the systems cater for many different types of package type, ranging from bare die through to butterfly packages or custom packages of that type. Technical expertise. YELO has shipped systems for 21 years now, photonics area. So we have huge expertise in the photonics game. And we've also supported systems dating back to 1991 in the field. So long-term support longevity is available from YELO. In terms of contacts, please visit our booth, Photonics booth, at that website there. Martin is my name. You can contact myself or my colleague Tanya, Business Development Executive. And our website is yelo.co.uk, and telephone numbers shown there. Thank you very much for joining. Thank you. Bye.